So welcome to part 2, History of Fluid Mechanics and Aerodynamics. And in the last lecture, part 1, we have discussed the evolution of mechanics that led to the branching around the early 18th century, where fluid mechanics started to emerge as independent field. And there was another branching around early 20th century where aerodynamics started to emerge in independent field. And this lecture is actually focused on this second branching on aerodynamics. I'm just here recapping what we have from part 1, fluid mechanics legacy, starting from Archimedes, buoyancy, Da Vinci, velocity area law, Galileo's pressure head, Torricelli law and experiment, Pascal principle and press, Newton's Principia, Bernoulli's hydrodynamica, D'Alembert paradox, Euler's equations of motion, Lagrange's particular solution in the case of what we call irrotational flow, Navier's equations of motion adding the effect of viscous shear stress, Poisson's equations deriving the same equations, Cauchy work on the kinematics of deformation, which are applicable to both fluids and solids, and all this culminated by Stokes' derivation of the most general form of Navier-Stokes equation. So this is pretty much the legacy of fluid mechanics, and there was a parallel line for experimental validations or techniques, perhaps starting with Marriott's measurement of forces on flat plate, Robin's whirling arm technique, the experiments on the fluid resistance by Borda, Dubois, and the French Academy of Science, the committee of D'Alembert, Condorcet, and Bossuet, Poiseuille flow in a pipe, and finally Reynolds' characterization of laminar to turbulent transition. So this was the legacy that pretty much we discussed last time, and we finished or concluded by posing this question that is it mature or practical enough for flight? What else do we need to enable aviation? And from this legacy, as always the case, we typically have two branches. Yes, we have equations of motion, but they are complicated and we cannot solve them. But we can do some analysis. We can do some theoretical analysis. And on the other hand, there is always people, who are inventors, what we call tinkerers, inventors. They are amazing, have amazing talent in building and construction. They are not that experienced in the theory, so they draw lessons from practice. Typically, the second branch precedes the first branch, and in the case of flight, both came at the right time to enable the era of flight. And this is the taxonomy of today's talk. I'll start with the theoretical analysis, and by saying start I mean after Stokes, after this legacy of fluid mechanics. I'll start with Helmholtz. He was actually a physiologist and a mathematician, of course. So like Poiseuille and Boussinesq, he was interested in studying the fluid flow due to blood circulation. So in 1858, he developed three very important and fundamental theorems on vortex dynamics in inviscid flows. The first theorem says the strength of a vortex filament is constant along its strength. And actually, this vortex filament cannot end in a fluid. It must extend to the boundaries or form a closed path. And as you guys know from your undergrad lifting line theory, these two theories indeed, form the heart of the lifting line theory, a cornerstone. The third theorem actually goes back to what we called last time Lagrange's theorem, which showed that an irrotational flow cannot lose its property. If once irrotational, it will remain irrotational indefinitely. So he applies it to a fluid, a blob of fluid of vorticity. So a blob of fluid in an inviscid flow cannot lose its vorticity and cannot gain new vorticity. So as Toccati describes these actually theorems, they represent like indestructibility and uncreatability of vortices in inviscid flows. And then Lord Kelvin or Thomson, 10 years later, he developed the conservation of circulation in of a closed contour, in inviscid fluids. You guys are pretty much familiar with this equation in this course. We've used it several times. And actually, it's interesting to let you know that Amir in our group, he developed an extension in the case of a pitching airfoil, accounting for the no-slip boundary conditions, so accounting for viscous effects. So d gamma by dt is no longer zero. He relates it to the pitching angular velocity. So then Kirchhoff and Rayleigh, and actually the three of them, Helmholtz, Kirchhoff, and Rayleigh, they wrote 3 papers studying the flow around a flat plate at a 90 degrees angle of attack. Quite interesting work. They were trying to resolve D'Alembert paradox, in the sense they're trying to get the force acting on a body in a fluid. It should not be zero. And interestingly enough, they actually allowed for sheets of discontinuity that early, sheets of discontinuity from the sharp edges. So they managed to get forces without viscosity, just from purely potential flow kind of techniques. This is akin to what we call nowadays wake drag kind of thing. And 2 years later, Rayleigh wrote this paper, very important paper in the history of aerodynamics, as you guys may expect, flow around a circular cylinder. And aside from aerodynamics, actually this paper, is a part of the history of a very interesting story in the history of fluid mechanics and aerodynamics in general. So let's now digress a little bit. Let's leave our objective and go and discuss this story. It's quite interesting one, which goes back actually to Robbins in particular. This book, which sometimes people call it the first textbook of experimental aerodynamics. Actually, Euler was, liked the book so much, he translated to German and added much to it, to the extent it became 5 times larger. And he published it 3 years later under a different name. And here is Euler words himself. He's saying, I'm a theoretician, but I'm sure that theoretical results should be endorsed by experimental proofs. That's great. Unfortunately, however, circumstances prevent me from dedicating the necessary time to experimental investigations, like all of us. But Mr. Robbins' experiments with the use of the ballistic pendulum were so numerous, and the results obtained by him are so important that I think they will meet my needs, especially in relation to the study of the problem of motion of gun projectiles under the decelerating action of air resistance. And this is actually our interest here. So indeed, Robbins dedicated the second half of the book to study projectiles under air resistance, and he adopted the v-squared law for air resistance. He wanted to explain why projectiles deviate from their theoretical and intended trajectory, and here is his explanation. First, the projectile encounters aerodynamic resistance to its forward motion. So this is the usual drag that we know of that slows down the motion a little bit. So this is in the direction of the motion, opposite to it. Second, he's adding another category, so it's not in the direction of the motion. Second, it rotates about its longitudinal axis, thereby creating a degree of dissymmetry of flow. So he's alluding to the fact that when you rotate, you create asymmetry in the flow field, so you will get a lateral force. It's not in the direction of the motion, it's a lateral force, normal to the direction of the motion. And this, you guys know from mechanics, generating a force normal to the direction of the motion will change your direction, will deviate your direction, right? Centripetal force kind of thing. It seems that the Berlin Academy of Sciences did not know about this work, so they actually issued a prize 50 years after Robbins. They issued a prize to solve this problem, this very same problem of the deviation of artillery shells from their theoretical trajectories. And about 58 years later, so like more than 100 years after Robbins, Professor Magnus, professor of physics at the University of Berlin, and actually one of Helmholtz's teachers, he solved the problem, and he simply did this quite interesting experiment. A cylinder subjected to an air blower, okay, but it can rotate. So as soon as the cylinder rotates, he observed lateral deviation, a normal force to the flow in the direction where the rotational speed of the cylinder coincides with the translational speed of the wind. So this is what we know as Magnus effect, which is, if you rotate a circular cylinder, you will get a lift-like force. So this is what we call Magnus effect. And as you guys see now, it's indeed not Magnus, it's Robbins, which reminds us of the Arnold principle that we discussed in part 1 last time, that if you have an ocean that bears the name of someone, then pretty much it's not his or hers. At any rate, then really, considered the flow around the circular cylinder, the paper that I told you about. Interestingly, he was actually interested in studying why a tennis ball, when a player does a cut, it goes into a curved path. So he studied the flow around the circular cylinder, ideal flow, potential flow. So you can see complete symmetry here, recovering D'Alembert paradox, and then adding a rotation, circulation. So there should be a figure here. Let me see. That's okay. Anyway, so there should be a figure, showing you the effect of circulation and the asymmetry and the normal force coming from, adding a circulation. I mean, this is very well known. You guys are expert on that. So then this was followed by some experiments, Lafayette, France, Prandtl in Germany, Ryabuchinsky in Russia. So early 1920, the concept of Magnus effect was quite well known and understood theoretically, experimentally, and so and so. Then comes our man of the story, Anton Flettner, an amazing engineer, impressive inventor. He was actually appointed to the scientific staff of the Luftwaffe at the time. And here is one of his actually inventions, the tab. Yes, he is the guy who invented the tab. I don't know if you have seen this as aerospace engineers or not. If it's hard to move your flap surface, you can move a secondary surface tab in the opposite direction, and now your surface will be free. So your servo or stick is connected to the tab, moving the tab. It's a small surface, so you exert a little bit of force, and the aerodynamic force on the tab will move the surface for you. He was proposing this idea actually for ship builders. They, in the sense that, this is a secondary rudder to move a huge rudder for a huge ship. But they resisted actually so much because at that time, marine engineers, they had the misconception that even some aeronautical engineering students have nowadays, that aerodynamic or hydrodynamic forces are due to impact, not due to suction kind of thing. So anyway, so this was slowed down his invention, and as Ducati describes, but the still young aviation industry at the time reacted differently. It was so anxious to advance rapidly. It wanted new ideas and audacious solutions. And this is his Flettner's words. Quite interesting actually to look at. Look at this. He is saying, since prehistoric times, man has tried to utilize the forces produced by fluid flows. But even the windmill in most recent times has not progressed beyond the dimensions of the old Dutch windmill. While on the other hand, the water wheel has evolved into a modern turbine. The development of shipbuilding was rather slow, but on the other hand, the development of the airplane was very rapid. Why such contrasts? And he's replying, because in some fields man tried harder than in some other fields. And this means, therefore, that there are good reasons for being optimistic. The treasures of the world of fluids will not disappoint the persistent explorer. I think this is quite interesting. So just giving you a little bit of idea about how a sail works. So this is the boat, and here is the wind comes. The sail, like any aerodynamic surface, it's just a curved surface, a camber. So it gives you a normal force, a lift-like force, normal to the wind. Then at the bottom of the boat or the ship, there is the keel that doesn't see the wind, but sees only the motion of the ship in the water. So it gives you a force normal to it, which cancels the lateral force on the sail, and you just end up with the pure forward thrust force on the boat. So pretty much this is pure aerodynamics, right? Everything here is just a normal force, a lifting like force kind of thing, and we just learn a new mechanism to generate a lifting like force normal to the wind via rotating cylinder. So this man, Anton Flettner, proposed this idea, propelling boats and ships forward by rotating cylinders in place of a sail. And indeed, he patented the idea in 1922. Then after that, he actually convinced the Göttingen Institute, almost the best at the time in Germany, with their best wind tunnels, to do experiments of this invention. And 2 years later, he invited representatives from the Germania Werft. This is one of the biggest shipbuilders in Germany at the time. He invited them to Göttingen to see his experiments and convinced them about his invention. And having Professor Prantl and Bitz on his side at the time, he managed to convince them, and here he is. This is his first experimental boat. Quite interesting. And indeed, in the same year, October the same year, they finished building the first model, which they called the Bukau. And Tocati has a nice comment here, saying, for the first time in the history of shipbuilding, here it was in the Baltic Sea, a ship without sails or huge funnels. So in October, few months later, it made its first voyage from Danzig to Scotland. It was complete success. The press who followed this voyage, they unanimously praised this new invention. It performed very well in stormy weathers, even better than a regular sail. And not only that, 1 year later, it made a trip all the way to New York. And this is his own words. It was interesting to observe how in almost all classes of the population, not only among the scientists and engineers, but in all kinds of other callings, people occupied themselves with my invention. I saw and still see how in all classes of the nation, in spite of the present conditions, he's talking about Germany 1926, you can imagine, there exists an incredible enthusiasm and receptivity for new ideas. I consider this, I was ignorant of this actually, and I got so excited about it because this is a paradigm for something coming out of pure theory, Magnus effect, to the lab, to a product. Unfortunately, it's not typically the case. So, and you name whatever inventions and great inventions you like. The airplane, it wasn't like this. Wright brothers didn't know about the theory of flight before, right? I mean, there was no theory of flight before Wright brothers. They did it first, and then luckily we got the theory for them. The jet engine was also like this. There was no theory before the first jet engine. I mean, I give you another one more interesting. In 1947, just try to imagine, in 1947, okay, a C-54 airplane, it flew from Newfoundland in the East Coast here to England, more than 10 hours flight, completely autonomous, including taxi, takeoff, flight, landing, cruise and landing and taxi, completely autonomous. Someone pushed a button. 1947, this is before Booty, before Root Locus, before Nyquist, not to mention Kalman, controllability and observability, no control theory whatsoever, completely autonomous flight across the Atlantic. So it's always like this. It's always like the inventors come, not always, but most of the cases, inventors come, do the thing, and then we develop the theory to make it more robust and, a product. So this was the other way around. This is indeed a triumph for fluid mechanics and aerodynamics. It's an idea coming purely from theory and doing it all the way to a product. I'll have to stop here and, so that's enough about this digression, but it's quite an interesting story, I guess, about Anton Flettner's rotor ship. Going back to our legacy, we just added few elements, theoretical elements to it. We added Helmholtz laws of vortex dynamics, Thomson conservation of circulation, Rayleigh flow around the circular cylinder. All of these include potential flow kind of thing. Experimental results, we just showed Magnus effect, which is actually Rubin's. And again, one has to always mention Reynolds characterization, laminar to turbulent transition. So again, this is the legacy. We added the theoretical branch to it. It doesn't seem to add much, and we're asking the same question: is it mature, practical enough for lift? Is it sufficient to enable aviation or not? So let's look at it. What do we actually have? We have equations of motion, Navier-Stokes equations, quite complicated, cannot solve them, but we managed to do analysis. We have now potential flow theory, can do flow around a circular cylinder and some interesting shapes. And also there are practical lessons by inventors and tinkerers we did not discuss here. We're going to discuss in a second. And actually, here are a couple of very interesting or very important lessons from this practice. Wind tunnel measurements by Phillips, and a few years later, the Otto Lilienthal's gliding efforts, they both concluded that curved surfaces are better. If you add camber, what we call camber in our language, this is better. You get lift at zero angle of attack, and sometimes you get better lift to drag ratio. Seems to be crucial findings for enabling aviation. At the time, this is more than 50 years after Reynolds, and many years after Navier's equations of motion. I said Reynolds, I meant Stokes. I always mean Stokes. So this is about 50 years after Navier-Stokes equations, and no theoretical explanation for this very simple facts that you guys do in your homework problems. So here is, just to give you an idea, here is Richard Ferry's book, How It Flies. This is a late date. So by that time, the community had already known why this is the case, the effect of a camber. But he pretty much was reporting the state of knowledge in the late 19th century. So look what he's saying. Later investigations have proven that the upper surface of the aeroplane must be convex to gain the lifting effect, camber kind of thing. This is one of the paradoxes of flying planes, which no one has been able to explain. So actually, this is why Kutta, a pure theoretician, indulged into the problem. He was just interested why a curved surface can give you a lift force at a zero angle of attack, almost complete symmetry. So I'm just trying to tell you that Navier-Stokes equations alone were almost futile, fruitless in enabling a theory of flight. We cannot explain the very basic things here. So what then enabled the theory of flight, or enabled the aviation? What is the theory of flight that enabled the aviation? This is what we're trying to touch upon here. But let's first talk about some practical lessons, because this is indeed what preceded the aviation, preceded the theory of flight. It's kind of slow. So we will start with Lomonosov. He's, like, if you want to say, the father of scientific enlightenment in Russia. And Tokati, as a Russian scientist, he got quite upset and resentful of the fact that almost all Western books on history of mechanics neglected and ignored Russian contributions. And this is a list of books, none of them included, or discussed contributions of Russians, which is a bit shameful. But at any rate, so he's actually has a funny comment here. He's saying, but Russia is far too big a cake to be belittled in this or any other way. That was quite interesting. At any rate, Lomonosov was a great scientist, physics, chemistry, gas dynamics, and here I'm going to give you one of his contributions to aerodynamics. In 1754, he actually constructed a meteorological observatory to study the properties of atmosphere. But the issue was how to deliver, how to elevate the components, the equipment that will do the experiment at different altitudes, different high altitudes. So he invented this machine. This is, as you can see, this is pretty much blades of a helicopter, and these two sets of blades, they rotate counter to each other. It's pretty much like a coaxial helicopter. So, and they run by a loaded, so we have a preloaded spring, and as you relax the spring, these two run, or they rotate opposite each other, and this thing screws up in the air. And depending on the stiffness of the spring and how much you preload it, this determines the height. that's quite interesting. And actually, here is minutes of meeting. He was consultant to the Petersburg Academy of Sciences. This is their minutes of meeting. Here is Lomonosov himself discussing his invention. Now, Your Excellencies, what you have just seen with your own eyes proves at least three things. First, the air, which we don't see, is real enough to provide support to the wings. Second, the design and construction of an aerodynamic machine is a practical proposition. Third, the direct study of the upper layers of the atmosphere is no longer an academic dream. And here is Tukati's comment that it is up to the historians of aviation to decide whether Lomonosov was indeed the creator of the first helicopter and the inventor of counter-rotating propellers. And as you can see, this is indeed the case. I'm reminding you of Leonardo da Vinci's invention that was not successful, was not tried. This one was quite successful. And something also to mention, this is in the middle of 18th century. This is like many years, almost 60 years before George Cayley. George Cayley, on that book, he made what I believe to be a very fundamental contribution to aviation, in the sense of this principle, that the problems of lift and thrust should and must be separated. Look at this. So these tinkerers and inventors at the time, or even scientists, both were inspired by birds, and birds fly by flapping. The flapping mechanism produces both lift and thrust. That's fine, but this cannot be scaled. So a crucial part here is that to separate lift generation from thrust production. You can get your lift by fixed wings fine, and then use an engine to get your thrust. So this separation was a key in the success of aviation. Indeed, he was skeptical of the role of theory. He said, no, this is too hard for the theory to play any role. This is his own words. I fear, however, that the whole of this subject is of so dark a nature as to be more usefully investigated by experiment than by reasoning. Reasoning means theory. And in the absence of any conclusive evidence from either, the only way that presents itself is to copy nature. Accordingly, I shall instance the spindles of the trout and woodcock. This is his own sketch measuring a cross-section of a trout. And if you just compare it, this is his sketch again, and this is just a NASA 6 series airfoil, pretty modern airfoil, laminar flow type kind of thing. So you can see, the similarity here. And so you can say that the concept of an aerofoil, we indeed owe it to George Cayley. And this is von Karman's comment that the principle of the airplane, as we know it now, that of the rigid airplane, was first announced by Cayley. Then things started to become more and more serious, systematic experiments. So this is when the founding member of the Aeronautical Society of Great Britain at the time, he designed the first wind tunnel for the Aeronautical Society, and several years later, Phillips developed an improved one. This is the one where he learned that curved surfaces are better. And then a few years later, people like Tsiolkovsky, Ryabuchinsky, Joukowski at Russia started to also build wind tunnels, and we have two big schools in Germany and Russia at the time. And pretty much the first decade in the 20th century, many countries started to build wind tunnels. So Krukov in Italy, Prandtl in Germany, Ryabuchinsky in Russia, Eiffel of the Tower in France. Actually, interestingly enough, Eiffel was quite interested in studying air resistance. So he used to drop cylinders from his tower, on a guided cables to measure air resistance. Okay, these are the two sets of experiments and Lilienfeld's efforts that we mentioned already about curved surfaces. Not all of the trials were purely experimental. There were some people trying to develop also simple theories. Here is Charles Renard, developing a very important formula to determine, okay, what is the power required for lift? And this is what we call the power loading, power normalized by weight. It actually is proportional to the square root. This is what he showed of what we call the wing loading, wing normalized by area. And the proportionality constant was estimated 1 year later by Henry to be half using SI units. So with this scaling, one can try to study, can a man fly or not? And actually, Helmholtz was interested in this question. As a physiologist, he studied bird scaling with the very legitimate assumption that, or position that area goes by length squared, weight goes by length cubed. So he can relate the wing loading goes by cubic root of the weight, which actually is supported by previous data of bird scaling. But now, if we consider these elements and make the following assumption, which is quite legitimate, that the power available goes with the weight, this implies that the larger the weight, the harder the flight, and there is kind of maximum weight that you can go beyond and use your muscles to fly. So, and there is a famous anecdote in the German academic circles that Helmholtz once failed a student in an exam because he asked him to prove that, human flight is impossible. So, Tsiolkovsky in Russia also arrived at the same conclusion independently, that man will never be able to fly on his muscles alone. And he suggested a flying machine that has the shape of a rigid soaring bird with two propellers and his head rotating in opposite directions, learning from his predecessor Lomonosov, developing a forward thrust. And for stability, he is suggesting adding two surfaces instead of just the tail of a bird. There will be a dual surface, one for vertical and one for horizontal. This is his own sketch. Quite interesting. You can see here the propellers. This is pretty similar to what we have nowadays, right? This is propeller, and you can see even something like a landing gear kind of thing. Quite interesting. And so this is why Toccati commented that Tsiolkovsky produced the first aerodynamic configuration of an airplane. All these lessons were, and here's also, he developed the first wind tunnel in Russia. Like I said, all these lessons were actually culminated by the Wright brothers' success. So they were not professional scientists, and but they learned almost all these practical lessons of aerodynamics developed before them, and they were amazingly good at construction and building. They actually even developed their own small wind tunnel to do their own experiments. They did about 1,000 gliding flights to draw their own conclusions and practical lessons, which culminates in their successful flight December 17, 1903. And here is their famous statement after the success of that day, that we packed our goods and returned home knowing that the age of the flying machine had come at last. Let's look at this airplane a little bit and see its characteristics. So it has about 750 pounds, 500 square feet, so you can get the wing loading as 1.5 pounds per square feet. If you plug this into Reynolds formula, you get an estimate of the power loading. What is the required power? About 4.4 feet per second. And look at the engine that they used, 12 horsepower engine. They assume 66% efficiency, so you can get an idea about the available power loading. So you can see that it exceeds what was really required at the time. And this was actually conservative estimate by Reynolds. So this gives you an idea why the Wright flyer was successful, kind of thing. And not only that, also Reynolds earlier in the same year, he also concluded that for a piloted aircraft, the engine should be lighter than 17 pounds per horsepower. And if you look at the Wright flyer engine, its weight is actually about 15 pounds per horsepower. So the success of the Wright flyer does not come at a surprise. It pretty much satisfied all the requirements coming from the practical lessons at the time. But the question that I always like to discuss is, did the Wright brothers, did this particular successful flight enable aviation? Well, we can say it started aviation, it triggered aviation, it showed that things are possible, but I disagree that it enabled aviation. And this is quite an important statement because we here in the United States, our students, undergrads, are amazingly good, pretty darn good at building and construction. So they can pretty much build a whole airplane model without knowing anything about aerodynamics. Okay, so pretty much, of course, Wright brothers knew more aerodynamic concepts than freshman students here. And they think, oh, okay, so I don't need this whole knowledge. And this is quite an issue here because, yeah, of course, you can build an airplane model. You can build some airplane like this, and which lasted about 59 seconds in the air, the longest flight at that day. That's fine. You can push it a little bit here and there, few minutes, whatever. But you cannot reach the level of maturity that we have nowadays, millions of flight hours every year. You cannot reach that level without a theory. So Wright brothers reached it here without a theory, all practice. That's fine. You can build some prototype. I totally agree. If you are an inventor and know how to build things, you can build a prototype, a successful prototype. But to have it to the level of maturity, robustness, this needs an enabling theory. So let's see what was the enabling theory of flight. So an airplane, what's an airplane? An airplane is just a wing, right? This is the main lifting element. Everything else you can add or you can decide to remove. I mean, we can have just a flying wing, right? So, and a wing, the nucleus of a wing is just an aerofoil. So what does the two-dimensional theory give us about airfoils? Well, we know how to get the lift, right? It tells us how much lift you get. So this is a crucial piece of information because it tells us whether we can carry this airplane or not. And we know the effect of a camber. We know the center of pressure or the aerodynamic center, so we get an idea about the generated moment in order to achieve balance. And not only that, it tells you how to do the balance. So we get the effect of a flap deflection or a control surface, so we can control the lift and achieve moment and balance. And we have the three-dimensional version of it, the effect of an aspect ratio on the lift and drag, and also the rest of the geometry, the twist distribution, the camber distribution, the core distribution of the three-dimensional wing, how it affects the lift distribution on the wing, and that the elliptic lift distribution is the best, in terms of minimum induced drag kind of thing. When you look at this collection combined, you know this is our body of knowledge that we use in analysis and design. Where did it come from? It's purely theoretical. It's not experimental, it's not computational, it's purely theoretical. This is indeed our body of work. How did we learn about this? This is pure theory, right? So it makes you wonder why the community is now neglecting a little bit or belittling a little bit the theoretical role. It's quite interesting. And not only in analysis and also in design. You guys know how to design a camber shape or an aerofoil shape to maintain a desired pressure distribution. You know that the NS6 series was designed this way to maintain a constant pressure distribution, right? You did this in a homework problem. And using similar techniques, you can design airfoils to do specific things like lee-back airfoils and many design examples. The 3D is much more interesting in the sense you can indeed tailor, a wing, twist distribution, core distribution, plan form to do minimum induced drag, minimum root bending moment, good stall characteristics like prevent tip stall kind of thing. Many things that you can indeed achieve. Here is von Karman's statement that the wing theory became the very basis of the scientific design of all our airplanes. And if you don't like von Karman because he is just a professor at a university, well, you can listen to this gentleman, Chevelle. He is the chief aerodynamicist of Douglas aircraft. He was the chief aerodynamic designer of DC-9, DC-8 in the golden era of aeronautical engineering. And when he retired, he went to Stanford to teach airplane design. Okay. So he wrote this paper in the 80s where the CFD was at the hype. He was recalling the technical challenges that he encountered during his career as a chief aerodynamicist at Douglas, building these airplanes. And, recalling a technical challenge, he would pose this question. Would modern CFD have warned of these problems and provided the necessary solutions? And this was his, answer most of the time. Probably not, probably not, probably not. He believes that these theoretical tools, enabled them to do amazing jobs. Look at his amazing tasks. Look at his own words when he was recalling the stall characteristics of DC-9. When the airplane flew, excellent pitch down and roll control were demonstrated at the stall, leading the aerodynamicists to ponder their brilliance. So indeed, these theoretical tools enabled. This is a chief engineer. I mean, who else should we listen to know what was the necessary tools that enabled their success? Indeed, these tools were in the pocket of every airplane designer and chief engineer, not only in pure aerodynamic analysis and design, also other aspects of aviation like flight dynamics, for example. What's the first step to do flight dynamics analysis? Well, stability derivatives. How do we get stability derivatives in our undergraduate courses? Say CMQ. Well, the airplane pitches, so we get an induced angle of attack, a change angle of attack on the tail, and we use this very same equation to get the change in the left, right, due to this change in angle of attack, or the three-dimensional version of it. So we use these two very same theories to get the stability derivatives, and once you have the stability derivatives, then you can get and do flight stability analysis, get the eigenvalues and check if they are in the left half plane stable or not, and do sizing of the horizontal tail, vertical tail, dihedral to adjust your stability, and indulge even more in the flight dynamic modes, short period, phagoid, Dutch roll spiral, and so on. And if they are not satisfactory, then we can design autopilots, stability augmentation and control augmentation system, because we know the effect of a flap deflection, a control surface from the theory. This is the B matrix in control kind of thing. So this all comes from the same two theories. And not only that, when we have aeroelasticity, how you get a fast expression for your divergence speed or control reversal, it's the same two theories. Unsteadiness, the whole business of unsteady aerodynamics, to tell you how your lift will build up from 0, say, to this very same value, dictated by 2 pi sine alpha, right? And if you have unsteady aerodynamics, you do flutter, you do flapping flight, you do all sorts of things. So indeed, these two theories were the enablers for aviation, and in particular, it's the two-dimensional one, because the three-dimensional one, incorporates it in the sense that what is the lifting line theory? It just tells you that any airfoil section, behaves according to the two-dimensional theory with just a change, a less angle of attack, simply. That comes from the tape vortices. So this is the heart, this is the root of aviation, this theory. So let's now discuss its evolution. Two-dimensional theory, 3 men, and the three-dimensional theory was developed by 2 men. It's the other way around. This is the first man, Lanchester, super professional engineer, automobile builder at the time. Von Karman described him as amateur mathematician. I don't like this, but that's fine. He actually founded a motor company at that time. And just to let you know about the qualities of this man. So he founded this company. So he's a practical engineer. He's not a professor at university. And he's doing, he's building cars. So if you are telling me that he is also building airplanes while building cars, that's fine, makes sense. But he's developing a theory of flight. So you can say around the same time, actually even before, he was giving a lecture to Birmingham Natural History and Philosophical Society. Part of this lecture was on his theory of lift. So he collected his work. Actually, he is the only one who worked on the two. two-dimensional and three-dimensional theory. So he collected his ideas both on 2-dimension and 3-dimension, submitted to a paper to the Physical Society of London. Unfortunately, it was rejected. And this is quite disheartening because it deprived him of priority. When I ask you, too few people know that Lanchester did something to the two-dimensional theory, right? So his ideas were here, and by the time he collected his ideas and published 2 books later on, by that time, Kutta and Joukowski have already published their efforts. So what's his contribution? You can get his contribution when you see his sketches that show circulatory flow, which means that we get lift due to circulation, and also show the Kutta condition. So this is one of his sketches. He was trying to do flow around the circular arc camber. This is the camber, just highlighting it. As you're going to see in a minute, this sketch alone is sufficient to determine completely the flow field and the lift forces. So look at his words. He's saying that the leading and trailing angles are conformable to the lines of the flow. The flow comes smoothly and goes off smoothly. Kind of the Kutta condition, what we call the Kutta condition, is satisfied at the 2 edges. And again, in his words, neither edge shall give rise to a surface of discontinuity. So, like I said, if you're expert in potential flow aerodynamics, this sketch alone is sufficient, indeed sufficient, to determine the flow field and forces. He is the one famous with replacing the wing with a bound vortex, taking the wing as a vortex. We're gonna discuss this in more detail in the 3-dimensional version. I'm gonna skip this. So the second man is Kutta. He was a pure mathematician, and he just got interested in the problem of flight because he wanted to explain mathematically why a curved surface at 0 angle of attack can give you any lift. And this is the paper where he explained this, did the flow and computed the lift on a circular arc camber to compare with Otto Lilienthal's results that show better lift when you have a camber, a curved surface. He actually did a small mistake here in his comparison against Lilienthal's, because of course Lilienthal was 3-dimensional, right? An actual surface in flight, in gliding, but his theory is 2-dimensional. And he didn't do correction because at that time there was no parental correction, is to come about 15-16 years later. But his justification was because the aspect ratio is around 3:4, so the 2-dimensional theory should be sufficient. Now we know that this assumption is not correct, right? But his determination of the flow and the lift was as we know nowadays. This is his own words, starting the paper, saying something like, if you consider a body immersed in a flowing fluid, the pressure forces acting on the body cancel each other out if we use incompressible, inverted, and irrotational D'Alembert paradox kind of thing. And since this does not agree with experience, then it must be the behavior of vortices that these are responsible for the pressure forces. So he's alluding to the fact that lift comes from vortices kind of thing. And this is his sketch, and again I'm telling you, this is very similar to Lanchester's sketch, and this is why I'm saying look at this. He's saying that the flow must be tangential to the arcs at both edges. Look at this. So he didn't explain this in his paper, but let's discuss it in our own language. Nowadays we know that lift is due to circulation. Okay, fine, we're gonna add circulation, but the ubiquitous question is how much circulation, right? Okay, and we know that without circulation there are gonna be 2 singularities at the leading and trailing edge. Okay, so what he is saying is that okay, fine, we can adjust the circulation to remove the singularity at one edge. Luckily, in this problem of circular arc, if you resolve the singularity at one edge, the other singularity is automatically resolved because of symmetry. So this is what he did. He found the circulation kind of thing in our own language to do this, and this is why this sketch is sufficient. If you have no singularity here and there and the flow comes tangentially here and there, this is sufficient because this gives you a Kutta condition, Kutta-like condition kind of thing. Interestingly enough, he actually have multi-element circular arc chambers analyzed, two interacting with each other. That was quite interesting in the same paper. But in this paper, he did not, he did not show his theory of lift that we know nowadays. His main focus and only focus was to get flow around the circular arc chamber. And I'll tell you why, because here, what they call his habilitation script, something like a thesis, he submitted to his advisor, Dr. Finster-Walder. In this thesis, which was unpublished, he has the entire theory of lift, rho u gamma, what we call Kutta condition explicitly stated, everything, as we're going to see in a minute. But the issue is, well, we can solve flow around the circular arc. That's fine. But now, if you have an angle of attack, either a flat plate or even a circular arc at an angle of attack, then if you resolve, it's not as symmetric. If you resolve the singularity at one edge, the other singularity doesn't get resolved automatically. So you have the luxury to resolve only one of them. And he was perplexed which one to choose. Why the trailing, not the leading edge, and why the leading, not the trailing edge. So he decided to not publish this work and just publish the part that he was comfortable with, which is the circular arc, because it's the very same circulation, simply resolves both singularities. But then Joukowski, on the other side, he published in 1906, 4 years later, his paper showing clearly rho u gamma kind of thing. We're going to see it in a minute. So at this time, his Kutta's advisor, Dr. Finster-Walder, he said, hey man, your stuff are being published, you should go ahead and publish them. So he published his seminal paper, 1910, that, it's a very long paper. I mean, not very, but 40 pages. Conformal mapping, rho u gamma, what we call the Kutta condition, explicit statement of it, leading edge singularity, suction force, how the center of pressure varies at the angle of attack, the entire theory of two-dimensional aerodynamics that we know nowadays. He published in that paper based on the recommendation of his advisor, and he was very concerned, spent too much time in the paper, big chunk in the paper, trying to work around this leading edge singularity. You can easily tell that he was really uncomfortable of this leading edge singularity, that the flow velocity goes to infinity at some point, and you have negative infinite pressure at that point. And his resolution was, well, you know what, no matter how sharp your airfoil, or if you have something here, it must be rounded. No matter how small it is, it must be rounded. And if it's rounded, then it will remove this singularity. So this was his justification. And at any rate, this was really good exercise. Why? Because this question would have been asked anyway in the following sense. Look at this. We have a flat plate at some angle of attack. That's okay. And now, if we neglect shear forces kind of thing, so all the force is normal to the wing, right? Normal to the to the wing, to the flat plate. But we're just saying that indeed the resultant force is pure lift and it's normal to the free stream, right? So this implies that there exists another tangential force that, together with the normal force coming from the pressure, they together give you the resultant force to be the lift rho u gamma normal to the free stream. So what is this force? So he actually, this is where he said, the leading edge is indeed rounded. No matter how you do it, it will be indeed rounded, and the negative infinite pressure here coming from the infinite velocity will give you a force here on, because it's now integrated on a finite, the very high pressure integrated on this finite, no matter how small it is, will give you a finite force. This force is called the suction force, and this is the one that we were looking for. So this was the genesis of the suction force, and this explanation, we would have needed it anyway, thanks to Kutta. And you can see here from his own statements, he's indeed, telling you about that the solution is indeterminate because the circulation is still arbitrary. There is arbitrary constant enters the solution, and this particular solution is determined from the physical requirement that no infinitely large fluid velocities should appear. And here is telling you that this is for the circular arc, we can remove it in both edges, but here in contrast, an infinitely fast flow around an edge can be avoided in problems of angled flow. If you have an angle of attack, only at one edge. Only at one edge you need to pick your poison. So he picked the rear edge, and this was smart. So Joukowski. When you look at Joukowski, indeed he's an analytical mechanics person, which I really like. So this is his master thesis, kinematics of fluid body. And look at his papers: stability of motion, impact of two bodies, theory of rotation of a solid body, pendulum theory, theory of gyroscope. He was a theoretical mechanics person to the extent Ducati described him as the Lagrange of Russia. So he was not pure fluid mechanician. He was an analytical mechanics person, similar to Lyapunov, similar to his contemporaries at the great time of Russia. This is the paper I told you about, 1906, where he indeed proved Rho gamma very clearly, very explicitly. This is his own words that that he is considering translational motion and motion due to parallel linear vortices. So he is superimposing U infinity kind of thing with vortices, and this is his own words again: the vortices annexed to the rigid bodies, they are attached to the body kind of thing. So here is I'm getting you from the paper. So this is px and py, the forces. Summation kn is summation, all the vortices in the body. This is our half gamma kind of thing. 2k is our gamma. And in 1910, so we already mentioned that Joukowski published the entire theory in 1910, right? So this was after, I said Kutta, right? Kutta. So this was after Kutta's paper in 1910. So it's independent from each other at the same year. A proof of Rho gamma, explicit statement of I don't know what to call it now. Is it Kutta condition, Joukowski? People call it Kutta-Joukowski condition because really contributed to independently by Kutta and Joukowski. And this is where he shows his airfoils, Joukowski airfoils. He actually started this paper by mentioning a paper by Professor Chaplygin in the same year, where he actually developed a theory that resolves the the singularities in all points in the leading edge by having a circle like Kutta, and this is in the same year, so you cannot say that it's really after Kutta, it's almost the same time. So same idea here. And in the trailing edge by the edge condition, Kutta-like condition. So this is why in Russia they call it Joukowski-Chaplygin condition. They don't call it Kutta condition. And in this paper, he also introduced his airfoils. This is his statements. Look at this. I have found two contours of airfoil form, two contours of airfoil form, two airfoil types, which give a flow with finite velocity. He means everywhere, because at the leading edge it's rounded, so no singularity, and at the trailing edge he satisfies his condition with Kutta. So this is the genesis of Joukowski airfoil. And this is indeed, the summary of the theory of the two-dimensional aerodynamics that enabled the flight. Let's, recap it. It started with Euler's equations of motion, right? Because then D'Alembert and Euler, they pointed to the very interesting special case where we have, this is an exact differential, meaning a potential flow. And then Lagrange's solves this special case to give you how to get the pressure in this special case. Just go and figure out, you know, the velocity field or the velocity potential and come here to get the pressure. Easy for you independently. And then Rankine used this formulation perhaps for the first time. He assumed doublet distributions to get the flow around oval shapes, Rankine body kind of thing. Rayleigh did a very similar thing to do flow around a circular cylinder and also plus a vortex to get a lifting like force. Up to this point, we can do flow around few interesting shapes, circular cylinder among one of them. But how to proceed further? It's not obvious at all how to proceed further. It's not. So there was a very useful tool developed, you know, many years before that can now play a role. Conformal mapping. Riemann mapping theorem tells you in his PhD dissertation that we can do mapping from unit disk to whatever. So if you can do flow around circular cylinder, we can do, you know, flow around whatever shape you like. There exists a mapping. It's just we're sure that it does exist. Just go and find it. So this whole theory is now almost ready to do, but there is a punchline without which almost this entire analysis, this entire body of work would have been almost futile, almost fruitless, in the sense that from a lifting perspective, in the sense that I can use this entire body of work and give you the lift 1000 Newton or 10 Newton, 0.1 Newton. I have no idea whatsoever about the generated lift. So this is the condition that presents itself very prominently. This is indeed the punchline. This is the secret here. This is the what I'm trying to say. I need a very strong word. So Kutta condition is indeed the key to get how much lift is generated, and once you have it, we're done. You enable your entire theory. This is why I'm always, as you guys see in the course, I'm always obsessed with the Kutta condition, because as you see from this evolution, without it, you can do whatever you like. You know a definite answer using potential flow. And this is Kutta's words himself. This assumption, meaning the Kutta condition, is completely false. If the angle is large, the angle he's referring to is the angle of the circular arc camber, which meaning that if large disturbance, large H to C kind of thing, large disturbance, this would not work. So this is his own words, the man who invented the thing. And of course we know that, and also we know that it's not applicable to unsteady flows. So it's just applicable to small disturbance, you know, small angle of attack kind of thing. And this is why we really are focused in our group, Cody, Gonzalez, Nabil, and I, trying to focus to get an extension of the Kutta condition, because it doesn't come from a principle. It doesn't come from F equals ma kind of thing. It doesn't come from a principle. And interestingly, actually, Cody has just found that you know, the steady version of the Kutta condition is actually a restatement of Gauss' principle of least constraint. So it comes from we now have a principle. And if we have a principle, there is a potential that we can extend things to high angles of attack or unsteady flows. I'm going to move now to 3 dimensions. And like I said, 3 dimensions, it's 2 men only. And the only one from the 3 men worked on the 2-dimensional, continued working on the 3-dimensional is Lanchester. He is the one who came up with the idea to replace the wing with a bound vortex. If lift is due to vortex, and I can replace the wing with a vortex, then it must really behave as a vortex. In the sense, it must induce velocity in the domain as if I have a vortex. Not only that, because Helmholtz's laws of vortex dynamics just told us that a vortex filament cannot end in fluid. So this means that the bound vortex cannot end at the tip. There must be something at the tip. So it will continue. It can change direction, that's fine, but it will continue in the form of free tip vortices. Indeed, they are called Lanchester free vortices. And like I said, So this is the induced velocity coming from the tip vortices. He was the first one to relate the kinetic energy of this induced velocity, the downwash due to the tip vortices, this kinetic energy to the drag, induced drag. Remember, in two-dimensional airfoil, if we ignore friction in two-dimensional theory, we don't pay money, we don't pay drag to get lift. Lift is free. In three dimensions, not the case. We pay money. We're ignoring friction, still ignoring friction, but we pay money to generate lift. This is the induced drag. He is the first one to, point this out and even relate the kinetic energy of the downwash to the induced drag concept. And this implies the following. If we don't pay money in two-dimensional and we pay money in three-dimensional, it means that the larger the aspect ratio, the smaller the drag we pay. Again, he is the first to determine the role of the aspect ratio, recognize the role of the aspect ratio. Here is the variation of the CL alpha of the wing with the aspect ratio. This is Prandtl lifting line theory, and this is Lanchester. He was underestimating the lift, but when it comes to drag, he was close to Prandtl. And this is because at the beginning he didn't, it was quite interesting because Helmholtz is 3 laws in the same paper. So he is using the first law, but the second law, actually he's using the second theory. The first theory tells you that, okay, if this is a vortex filament, one comes here along the wing and one comes here. If this is the same vortex filament, it must be constant, right? So this gamma must be equal to the same gamma here. He did not recognize that and took him several years to recognize and revise his model. In 1915, still before Prandtl, 3 years before Prandtl, he arrived at a formula for the induced drag exactly as Prandtl's formula. And you can see it as early as even 1894, like 20 years before Prandtl, carrying a wing with an elliptic shape. Here you can see it, but he was pretty much inspired by birds. And this is Prandtl's. So von Karman, Prandtl was his teacher. So von Karman praised him a lot, and let's look at this. This was quite interesting to me. He's saying his control of mathematical methods was limited. I didn't expect that, actually. So it was quite interesting, frankly speaking, encouraging. Many of his colleagues and followers surpassed him in solving difficult mathematical problems, but his ability to establish systems of simplified equations which expressed the essential physical relations and dropped the non-essentials was unique. I believe even when compared with his great predecessors in the field of mechanics, men like Euler and D'Alembert. So yeah, you can see it's all about, when it comes here, it's all about physics. He was actually son-in-law and student of Professor Fupel at Manchester. And this is actually a common tradition in German academic circles. Lifting line theory. If I ask you who invented it, many people would say Prandtl. It's Prandtl's lifting line theory. As you can see, unfortunately, it's indeed, we should not ignore Lanchester indeed. And this created actually like a schism in the community, a debate. Who is the lifting line theory should be attributed to? And people started to blame Prandtl that he is not paying, dues to Lanchester's contributions, and he is addressing this point in his, Wright Memorial Lecture to the Royal Aeronautical Society. This is his own words. It's quite interesting. Let's read it together. In England, you refer to it as the Lanchester-Prandtl theory, and quite rightly so, because Lanchester obtained independently an important part of the results. He commenced working on the subject before I did, and this no doubt led people to believe that Lanchester's investigations, as set out in 1907, his Aerodynamics book, led me to the ideas upon which the airfoil theory was based. But this was not the case. The necessary ideas upon which to build up the theory, so far as these ideas are comprised in Lanchester's book, had already occurred to me before I saw the book. In support of this statement, I should like to point out that, as a matter of fact, we in Germany were better able to understand Lanchester's book when it appeared than you in England. English scientific men indeed have been reproached for the fact that they paid no attention to the theories expounded by their own countrymen. whereas the Germans studied them closely and derived considerable benefit from them. The truth of the matter, however, is Lanchester's treatment is difficult to follow, since it makes a very great demand on the reader's intuitive perceptions, and only because we had been working on similar lines were we able to grasp Lanchester's meaning at once. If you look here at Toccati's comment on Prandtl's contribution, the 1918 paper of lifting line theory, he is saying that his work was accepted by the community as the satisfactory sum total of all previous contributions, mainly because of its mathematical simplicity and clarity. Von Karman's comment, Prandtl systemized the ideas in a simplified picture. So I think it's super clear for you guys, myself, all the young generations, that it's simplicity and clarity. Otherwise, you will lose your priority, you will lose your contribution, people will not use your work, period. I don't know if I have time to go through the Prandtl lifting line theory because it's indeed, in the books. I love to discuss it, but one thing, he was actually perplexed to solve the integral equation here, so of his own theory, and this gives you that yes, he was not the best mathematician of the time. Beyond the theory of flight, I mean, there are too many things that should be mentioned, and unfortunately I don't have time, so I'll have to skip too many things and just focus on key things. Of course, the boundary layer theory cannot be skipped, so, and again, it's due to Prandtl this time. So at the finally, and even many years, as you can see, before developing the three-dimensional lifting line theory, this is the effect of friction now. He finally solved the problem that too many great men worked on: Newton, D'Alembert, Borda, Bessou, Dubois, Helmholtz, Kirchhoff, Rayleigh, Froude, many others. Finally, he is solving it based on the brilliant assumption that the viscous effects are confined to a thin layer around the body, what he called the Grenzschicht. Of course, my pronunciation of German as English, they are both not that good. So this is what they call the boundary layer, Grenzschicht. His student Blasius' PhD dissertation was in solving the boundary layer equations, getting the famous Blasius solution. Compressibility effects, again, Prandtl's student, accurate. He developed the supersonic theory, getting the effect of Mach number here. It's 4 alpha divided by this famous factor. You guys also know Prandtl and Glauert independently did a compressibility effect, subsonic. So this is the supersonic, student of Prandtl. The subsonic, Prandtl himself, the 2 pi alpha kind of thing, and this is the famous correction. So the 2 pi alpha in the subsonic becomes just 4 alpha in the supersonic. And too many, extensions in the three-dimensional of Prandtl lifting line theory in the wake drag by von Karman, also unsteady aerodynamics, because it's more relevant to this course. You guys should be experts on this now. Wagner, 1925, step response, Tudorson, 1935, frequency response, von Karman and Sears, many extensions. There is one that I really like to mention because it has an interesting story, Jones. This is von Karman's description of him. Jones is an example of a scientist who made great contributions to aerodynamics without having the advantage of systematic education leading to a degree. Jones attended college for only 2 semesters. Then he left and was building airplanes to a small company. Unfortunately, Great Depression came and he lost his job. Things went really bad. He ended up actually operating an elevator at a government building at Washington, D.C. And by the recommendation of the congressman of his hometown, he got a job at NASA. He was actually operating a wind tunnel at NASA. This is quite funny. But because he was super interested in flight, his supervisors at NASA allowed him to attend lectures and read reports. This was the golden era of flight, and do experiments in the wind tunnels. So he taught himself and became a theoretician. He developed theories. Here he was, this very famous paper, he was developing, approximations to Wagner's step response kind of thing. But ignore this. He actually developed a three-dimensional unsteady theory, one of very few three-dimensional theories in unsteady aerodynamics. And he even, have the audacity to extend parental lifting line theory to small aspect ratio kind of thing and delta wings. He became a theoretician developing theories. That's quite interesting. Many extensions after Jones. I'd like take the chance to mention our few droplets in this big ocean. We recently developed what maybe considered as the first viscous unsteady aerodynamic theory. And just trying to conclude here, is it really an old saturated field? Is it killed or what? I would say that what we know is actually very little. So for example, we have a theory for subsonic and supersonic, but we have no sound theory of transonic. And actually most of our flight is in the transonic regime. So we simply almost know nothing. And in the high alpha, look at this. This is my favorite one. I mean, I showed to you many times, guys, in my group. This is the CL alpha curve, right? Geometrically, we have up to 90 degrees. This is the little piece that we know. The rest of the curve, no sound theory. So this is a huge unexplored regime, huge potential here. But we should arrive at it with the right mindset, in the sense that typically we consider as a bad regime full of nonlinearities, unsteadies, and yada yada. We should approach it from following mindset, to exploit these nonlinearities and unsteadiness to our own advantage to achieve performance that cannot be achieved in a steady small alpha environment. Many actually groups are doing that nowadays, and we recently showed that you may get lift enhancement if you do unsteady oscillations here, plunging oscillation. You get lift enhancement that can be even up to 40% in the mean lift coefficient. So that's a lot. Also, if you look at the recent advances in fluid mechanics, unsteady and high angle of attack, you know that there is a lift enhancement in the dynamics, not the mean lift coefficient. Here in the stall, in the dynamics, in the frequency response amplitude. And if you go and look at the classical efforts by Garrick, you will immediately realize that the propulsive efficiency of flapping is actually directly related to this magnitude of frequency response. So if it's enhanced in the stall, you may get enhanced propulsive efficiency, something like around 95% actually propulsive efficiency. You can achieve that with very careful design of flapping propulsors near stall. And if you think about it, 95% propulsive efficiency, this will save 25% fuel consumption. This will save $25 billion for American Airlines per year. It can do great things. The 25% fuel consumption is unheard of. The winglet, which marked a hallmark in the history of flight, just saves 5% kind of thing. I think this will be enabled by unconventional, the need for unconventional configurations, and maybe the last questions that we need to touch upon is, do we still have business after the COVID-19, or we're just this is killed, we're out of business? Some people are pessimistic and yes, we're out of business, and some people are optimistic, saying that it's just more challenges, in the sense that you just need your airplane to be much more efficient, to have the luxury, the room to account for health precautions, whether it's enlarged spaces between passengers, whether it's new system, whether it's completely new configuration. You just need to be ready, in the sense your airplane needs to be much more efficient than before to account for these new health precautions. I'd like to thank you and stop recording here.